So in this episode, we're going to talk about interfacing with the analog world. And we're going to begin our discussion by going all the way back to the very first lecture where we talk about digital versus analog. So let's just briefly touch on that, and then we'll get into how we can interface with the analog world, which is what this chapter is called. So this may look familiar to you. These are slides from the very first lecture from chapter 1. And so if we just take a step back and look at both systems, digital uses on and off states that can be represented using zeros and ones respectively. Okay, analog is continuously varying, and so the temperature outside, the temperature inside, the air pressure, the pressure inside of some system, the velocity with which some object is moving. So there's all kinds of different analog systems, and matter of fact, most signals and most physical quantities in the world are analog. This means they have an infinite number of value possibilities. Okay, so you can look at any point in time and you can get down to the nanosecond, picosecond. You can take it out as far as you want, down to any point in time throughout all time. Okay, so that's an analog signal. A digital signal represents an analog signal by using sampling, right? And so representing a certain voltage level or a certain amplitude from the analog signal as a digital value. So right now, typically if this was a face-to-face interaction and there were no devices used to sample and transmit, if it was just two humans standing in front of each other, those are analog signals being traded back and forth. The sound of my voice right now, although it's analog in nature where it originated, where I'm sitting right now, but once it finally reaches your speakers and then to your eardrums so that you can hear me, it's gone through quite a transformation, hasn't it? So it gets sampled into the computer that I'm working on, and every time my voice has a certain inflection, it's sampling a very, very fast rate to represent my voice in ones and zeros, essentially. Okay? So in industry, devices like transducers are used all the time to take some analog physical quantity, like temperature, pressure, velocity, whatever, and convert that signal into a digital, or convert it into a voltage, which then can be scaled to represent a certain digital value. And so, therefore, you can have different digital values representing different points in your conversion, right, from the physical quantity into a digital quantity. So once again, to show the difference here, here we have an analog watch face, where presumably we've got some gears inside of here that are clicking and turning and are working in real time. And so you're seeing the actual seconds tick by here in an analog format. There's not very good resolution in terms of, here's 12, 1, 2, 3, 4. We don't see any tick marks in between there, so we kind of have to guess where it's at, right? Here, we have the exact time. It is 8 hours, 32 minutes. Okay, now I don't know if this is AM or PM. Doesn't really matter. But it's 8:32 and the date is 11:27, and those things are generated, as you know at this point, by counters. You represent the voltage as either a high or a low. Okay, here continuous smooth changes with the analog signal. There is no sampling going on. If for every point in time here, there's a voltage that's analog here. Here, you could try to pick a point in time that's in between 2 points of a sample. You'd have to magnify that, but you could possibly have that happen. So with a digital signal, it's all about how quickly and how accurately you can sample an analog signal and convert it. Okay, digital watches obviously very, very popular. There's been statistics that say that by a certain year, some students won't even be able to recognize or be able to read an analog face. I don't know how true that is, but it's a whole lot easier to determine what the time is. And Most smartphones and tablets now, all you have to do is hit the power button just to bring your screen back on, and it'll tell you these two things typically, right? And you don't have to do the watch face. So we've been using this technology for a long time. Audio CDs and DVDs were really the introduction most people had to these types of systems, because prior to that we had 8-tracks and we had cassettes and we had video cassettes, but with the advent of the CD and the DVD, now we were able to store those and sample them quickly enough to where they almost had essentially a lossless format. Now there's people that say they can tell the difference between an analog recording and a digital recording, but as quickly and as accurately as they can sample things these days, it's pretty hard to tell the difference. I guess you would have to have some pretty good speakers or be an audiophile yourself to be able to tell the difference. Now I'm not talking about lossless quality versus like a WAV file versus an MP3 that was compressed. I'm not talking about those type of quality differences. I'm talking about if you were to put on a vinyl record, let's say, through a nice system, and then compare it to a lossless WAV file, say, or I think there's FLAC, FLAC. That's another type of music file, and so there's technology out there that can make it sound almost as good, or some people say it sounds better. So I guess it just depends on the person. But long gone are the times where we carry around physical media, to watch or to listen to whatever we want, right? So now we have all of that stuff on our phone and we can stream, and most folks don't even own physical media anymore. They just subscribe to some channel or some app, and they can get everything they need without having to physically store anything or have to replace one because it gets scratched or it gets broken or stepped on, or just with old age, audio CDs and DVDs will start to go bad, and they do have a shelf life of about 30 years. So this is a good example of what you might see if you're going to convert an analog signal to digital. You have to have some type of scaling mechanism, and we'll later find out that that's called resolution. How many bits do you have to represent this signal? Well, it looks like in this case we've got an entire byte here. We've got 8 bits. So you could have from 0 to 255. So 256 different points from whatever the tallest point is here to 0. So you could chop that up 256 times and get pretty close. Once you cross a certain voltage threshold, you uptick on what the binary count is that represents it. Now it's not doing this here. It's saying that this one's at the top. So I'm not sure how this is scaled, but I'm just saying that's one way that you could do this. So just to reiterate what's happening, it's something similar that's happening right now. It's not going through the same process, but it's still taking an analog signal, which is my voice, converting it to a digital signal. The digital signal is processed by my computer. The computer then sends that out over the internet as a series of ones and zeros in a certain order with a certain protocol. It ends up wherever you're streaming this from to your computer. It takes that digital information, converts it to an analog signal out of your speaker, and then either through your earphone speakers and vibrates the sound in a way that you can hear what I'm trying to say, or you would have speakers on your desktop that you would use. Okay, but it's going through that process. It gets processed into a digital signal so it can be sent, and then it's converted back to analog and then amplified through a speaker. And just to also reiterate why digital systems are typically immune to analog noise. Remember, with a digital signal, you only have 2 possibilities, on or off, 1 or 0, 5 or 0, 5 volts, 0 volts. Okay, so even if you're at a low, okay, or an off, even if you have a little bit of static and noise, that still looks like an off. Until if you had a big enough voltage spike, then yes, you would cross the threshold and you would cause an error. Okay, but that's why we have parity and error checking for that kind of stuff. When you're at a high and you get some noise on the line, if you're at 5.1 volts or 4.9 volts, that's still a high no matter how you look at it. Here, if anybody's old enough to remember the old rotary type phones where you had an analog signal and it wasn't through these digital networks, if somebody could actually cut in and out, like if they had a cordless phone and they got too far away from the receiver, and so you could actually hear them go in and out and cut in and out. So digital signals, it either works or it's not working. There's usually no garbled error on there. It's either working or it's not. Kind of like with the digital TV. The digital TV either works or it's completely pixelated and you can't make anything out. Whereas with an analog signal, the old analog TVs, you could keep adjusting the rabbit ears. And I know that digital systems have something similar because you're still grabbing a signal out of the air. But with the old analog signals, you could add foil to the, increase the surface area which the signal could hit, by adding a little bit of foil. I don't know if that really did much. I've never studied it, but anyway, you could keep adjusting it and kind of see it and kind of see where the noise is filling in the spots, and then you could just get it right in the perfect spot where you grabbed a good, nice, strong signal and it would block out all the other noise. Okay, so that's not what happens typically with digital systems. It either works or it doesn't. So fast forward to the current chapter, and we're going to start our discussion by talking about what is used most often in analog to digital and digital to analog converters, and that is an op-amp. So to start our talk about the op-amp, the first thing I'm going to point out is the fact that we are going to assume that there is a very high input impedance between the two terminals here. Okay, this is essentially set up like a comparator. So very, very high input impedance on the front two terminals, and essentially we can assume that it's nearly infinite. That means that this becomes essentially a virtual ground. Now, I say virtual because it can't sink current like this ground can. So this is a virtual zero. So if that's the case, and this is a virtual zero, that means that this positive 12 across this resistor is going to give you 12 volts divided by 10k ohms. That's going to be a 1.2 milliamp current coming into this node. This part of the circuit over here, this is positive 10 volts dropping across the 5k down to this 0 volts. So that's 10 volts divided by 5k, that's 2 milliamps. So we've got 1.2 plus 2, so we've got 3.2 milliamps coming into this node. So I just said we assume that there is a high impedance on these two terminals here, so we can't sink the current through this terminal, so it's going to come up and around. So ultimately we want to find out what V out is, okay, and it's going to reference what happens back here because these are going to add together and then go through this resistor up top. Okay, and so that's going to give a voltage drop, whatever this current is. In our case, it's 3.2 milliamps. So 3.2 milliamps times 2K will give us our V out. So you can see here, so 1.2 milliamps from this source and this resistor, 2 milliamps from this source and this resistor. So the equation to find this V out, and sometimes you just have a single source and a single resistor. Here we had two that combine together, and we know through KCL that those add together, and because it can't go in through here, all of it goes through the feedback resistor. So it's negative I, where I is this resistance or this current going this way, times the feedback resistor value. So this is 3.2 milliamps times 2 kilo ohms. And again, there's a negative sign out front that gives you negative 6.4 volts. So if that's the case, and we can sum different branches together to get a bigger current to go through this feedback resistor and change the output voltage, we can use what's called a binary weighted digital to analog converter. Okay, so this is where we have In this case, this is a 4-bit system where we're representing a, from 0000 to 1111, so 0 through 15, and depending on which of these switches has been connected, that's going to correlate to a certain voltage output that's going through this 20k ohm resistor. Now notice the way that this is set up. So we have a 5-volt digital in here, and again, these switches are going to represent lows and highs. If it's a low, it's off, and if it's a high, it's closed. Okay, so we have 12.5, 25, 50, and these are all K, 12.5K, 25K, 50K, 100K. You'll notice that they all double each time. Okay, that way you get a good predictable, because it's going to be 5 volts divided by 12.5K. That's going to give you a certain current. 5 volts divided by 25K. So you're going to have a predictable current from each branch, and you can, when they sum together, that value will give you, a certain binary equivalent. Okay, or actually it's an analog equivalent for this digital set here. Okay, so we can represent all 16 of those with a different value, sending it through a comparator, similar to what is happening in the previous slide. And because you do have to double the size of that resistor every time, this isn't a really good system for anything that's greater than 4 bits. So anything up to 4 bits, I think it works fine, but if you're going to double again, now you're up into 200K, and then you'd be up into 400K, and now you're almost at a meg. So for 4-bit systems, they work great. Now to switch gears a little bit again and take you back to 111, or take you back to your first circuits class, and we learned about the R2R ladder network, and it had a very similar setup to what we saw with the binary weighted system. Okay, so if we do the same thing where every branch here we have a switch on it, and one of the if it's on one switch it goes to ground, the other switch is a high. Okay, so here we've got all of these connected together. So we have a predictable current that's coming down each branch. Okay, so as you can see here, commercial 8, 10, 12, 14, 16-bit resolution converters are common. So it's still playing off that same principle where we get to sum all of these branches together and send them through the feedback resistor and have a voltage change based on that. And just for further clarification, here are some of the markups that Kleitz has done. And so here he's saying that we start with a 500 microamp current coming into the node, which gets split 250 and 250, and then 125, 125, 62.5, 31.25. So again, depending on which one of these switches is high and is going to pass the current through, we just add those together, and that represents that digital value on these switches here. And here's a good representation of what you'd see on, like this is a 10 volt scale, and we're going from 0000 to 1111. And so you can see here, we have a certain voltage out for every one of these, and it looks like a staircase the whole way up. So we're actually going to look at some of the staircase generators here shortly. But anyway, you can see here that every one of these numbers is represented by a analog output. So one of the IC chips that's pretty popular is the DAC 808 and the MC 1408. They're common 8-bit converters. So you can see the general setup here. Here's from least significant bit to most significant bit, A8 through A1. And those are essentially all on current switches. They get sent through an R2R ladder network, and then it gets sent to the current amplifier. Okay, and then it has a voltage out. So if you're going to use one of these, it does have to have a reference current. Okay, and so this one is for 8 bits, and it's scaled from 0 to 10 volts. Okay, so 2 amps is the reference current, and we get that from the 10 volt reference voltage and the 5k ohm resistor. 10 volts divided by 5k, that's how we get the 2 milliamps. So that 2 milliamps is the full scale output of these digital inputs, A8 through A1. That means if it's not at full scale output, if it's somewhere in between 0 and full scale, then you're going to use this equation right here, so the output current of this MC1408, the DAC application here, the output current is going to be the reference, so 2 milliamps, and then some portion of it, right? So it's always going to have something in the denominator here. It's always A sub n over 2 sub n. So for this one, this is going to be bit A1 over 2. So it's the same kind of idea where we're adding on a known quantity, and so here you're trying to get some percentage of the reference. Okay. This capacitor down here between pins 16 and 3, this is more of like a noise canceller, so to speak. That's what it's doing down there. So again, you can see here we're using a 741, which is a common op amp, LM741. And so you can see here the analog voltage out, again, I out, right? Now, it's not using the negative here. The negative is implied last time when it's coming back this way, okay? So now we have a positive voltage if it's going to be sunk back this way, okay? So one way that we could simulate this is to have a DAC set up here, right? So we're taking a digital input on the left side here and converting it to some analog output that we're then going to put into an oscilloscope. So this is a 10 kilohertz clock oscillator, and we're assuming that everything is just going to keep counting higher and higher and higher and recycle itself. We don't have any reset circuitry here. So whenever this one goes, we're going to activate this 7493. So we've got 2 of them here. So these are 16-bit counters, each one. And so, I'm sorry, mod 16 counters. So 10 kilohertz signal in here. This will cycle through, count through all of these, all the way down to 11111, and then it'll recycle itself. So for each one of those counts, so where you have a unique input here from A1 to A8, that's going to correlate to a specific voltage output here, okay? Because that's where we're grabbing. It's right here. So we're actually going to be syncing this back through here and getting a certain voltage out. Counter out is one way that we can do analog to digital conversion. So essentially what we have is a counter that's used in conjunction with a digital to analog converter. We're going to take a look at a picture of one of those here in just a second. So it says to change for continuous conversions, end of conversion line is tied back to clear the input. The major disadvantage of using this is the slow conversion time, and you'll see why here in a second. So what we're doing is essentially we've got this comparator here, right here. We've got our analog voltage in. Remember, this is analog to digital, so we're trying to create a digital output from this analog input here, okay? So the first thing we want to do is we want to start the conversion. Hit this right here. That will allow this current to flow and give us a brief low here, which will clear the counter and will clear the 8-bit converter back down to 0. So what we're going to do is we're going to keep increasing the count, which is going to change the output of the digital analog converter to the point where this one will be equal to this, and then it will eventually try to surpass it. So over time, this thing keeps ramping up, ramping up, ramping up, ramping up until the point it gets to the same voltage as here, and then the comparator will output a low, and that will be the end of the conversion, and it will stop the clock and trigger the D flip-flop to go out to the output. Okay, so again, this will go low briefly. Okay, this is a negative edge trigger flip-flop, so wherever the D was here, these inputs get passed through. Remember, Q follows D with the D flip-flop. So when this activates on the negative edge, it's going to pull all these through to this digital output, and then it gets sent somewhere. Another one is the Successive-Approximation analog to digital conversion, which is similar to the counter ramp in that you have this sort of a feedback mechanism that's constantly checking to see if you have the right value. The difference is this is a much, much faster conversion than the counter ramp. So part of the reason this is quicker is essentially it's just checking each one of these output registers one at a time, 8 bits at a time, and then checking internally to see if the first line is high. So if D7 is high, it will register that over here, okay, in this output register. So it's constantly checking, trying a high at each one of these bits, and then determining whether or not it's a high or a low here. And so eventually you end up with a digital representation of whatever this analog voltage in is. So again, the previous example that we looked at with the counter ramp tries every single possible combination from 0 up to that number, whereas here it only takes 8 clock cycles because you're only checking a bit at a time to determine what the value is based on this analog in. Here's a nice example of a data acquisition system, which is super common in industry and in all types of sporting, especially like motorsports. They constantly have data that's being acquired from the vehicle, and then they're putting into these models to determine, tire wear and gas consumption, that type of thing. But in this system here, we've got some transducers. Again, a transducer takes a physical quantity, converts it into an electrical quantity that we can then scale and determine what that original value was. Okay, and we can scale it in almost any unit you can think of. Okay, so here we have temperature, pressure, displacement, velocity, fluid level, kilowatts, humidity, solar radiation. Okay. So we've got these transducers that are converting the physical quantity into some voltage. Most transducers are either 0 to 5 volts out or 0 to 10 volts out, or they could use 4 to 20 milliamps output. So they first come into this analog multiplexer switch, which is essentially a data acquisition piece that you would need here. So again, just to refresh, it's kind of like having a lot of different TV stations available that you pay for, but only being able to select one at a time to send it to the screen so you can view it. Okay, so again, that's what a multiplexer is doing. So it's selecting only one of these into the output, and that selector is based on these 3 input lines here, these select lines. Okay, so then that's sent to a sample and hold circuit here, and then sent to a programmable gain instrumentation amplifier, and then all of this stuff is talking back and forth to the microcontroller. So as you can see, after it leaves the final device here, the final amplifier, that is taken all the way down here to the analog digital converter, and that's being sent, here's the digital output into this data bus, and then that obviously has been taken into a certain port on the microcontroller. So in a previous life, I used to do all of this type of stuff where we would calibrate transducers, and this is really one of the only times I ever had to make some circuits to look at some of those transducers. If they didn't send any of the extra display stuff with it, sometimes I would have to create a small little Wheatstone bridge or something, depending on what the application was. But essentially, a transducer converts a physical quantity to an electrical quantity. So I looked at pressure transducers, torque transducers, all kinds of different, any physical quantity you can think of, and then converting that to an electrical quantity. And it says must be conditioned due to different output ranges and signals. The biggest thing that you have to look at is the manufacturer specifications. So you can actually damage this if you don't have the right signal conditioning and how you're trying to read it. Okay, so then you can take that data and then you can manipulate it with software. You can graph the output of it so you can see how it responds. One of these is the thermistor. And so you can see here, this is a nonlinear device. So the thermistor, you are completely dependent on the specifications that come with your thermistor. There's going to be some type of an equation that you plug different values in to figure out exactly what the temperature is. It is not a chart where you can go look up, like with a thermocouple. A thermocouple, you can look up on the chart what your millivolt reading is, and it'll tell you what the corresponding temperature is. Here, you have to know some other things to get the accurate temperature reading, but a thermistor is more accurate than a thermocouple. And you can see here, if you put that load in there, right, that's that sensor, that thermistor, and so obviously the resistance is going to change depending on the temperature. And if the resistance is changing, well, this voltage drop across these two resistors here, if this is changing, that current is going to change. And if that current changes, as we've discussed already, the current that's going through the feedback resistor will change, which is going to change the output voltage. So this constantly changing is going to adjust this output, and that can be sent and used to the VN of an analog to digital converter. Okay, but just a very simple circuit here where this resistor is going to change the current value, and it can be scaled depending on out to some resolution, whatever it is. And you can see here it says output voltage levels for a temperature range from 0 to 100 degrees C. So at 0 and 100 degrees, we have a different resistance here. So obviously the hotter it gets, the lower the total resistance is going to be. And the resistance of R sub I here, right? So that's this right here combined together. But really the variable is this. This is a static 10K. So really what we're talking about with Ri is the difference, the change in this right here, because at base it's going to be 10K. So anything above 10K is what we're adding on through this thermistor. So at 0 is when it's at the highest resistance, and when it's at 100 degrees, it's when, at least scaling it from this range, it's much, much lower resistance here. And so if you have less resistance, you're going to have more voltage drop because you're going to have a bigger current. Another gauge that we used all the time and we calibrated all the time is called a strain gauge. And so you have sort of this sort of a grid pattern here. It's not really a grid pattern, but almost looks like an exaggerated sine wave or something like that. But anyway, it's all connected together, and you have what's called a sensitivity axis. Okay, and so these can be used to measure weight. Like if you have a home scale that you use to check your own weight, that's more than likely got a couple different strain gauges inside there that when you step on the scale, it flexes this, whichever way the axis is that it's supposed to flex, and it's going to change the resistance. Okay, and foil type, they're very, they're not too awful durable. It depends on the application. Some of them are pretty stout, but they can be damaged, so you just have to be careful. Like if you step on a scale too hard, you could damage the strain gauge, and then it has to be replaced, or you have to replace the whole scale. So anyway, the resistance changed when this thing gets stretched in a certain direction. So here's a graphical representation, not a graphical, but a pictorial representation. So here, what we're doing is we're putting some flex into this metal beam. Okay, and that's going to change this resistance based on the travel that this moves in this direction for this force gauge. Okay, so it doesn't have to be a force gauge. This is just a strain gauge being used to measure force. So again, part of the reason why we study the Wheatstone bridge is because it's used so often in these type of applications, because essentially you have two voltage dividers, right? We've talked about this with Wheatstone bridges. You've got a voltage divider on this side, you've got a voltage divider on this side. That means that you can have a certain voltage here at B and a certain voltage here at A, and those can be fed into an amplifier. This one just has a gain of 1, and then take this out to an analog to digital converter. And what's going to change is this strain gauge right here. Okay, so here's the reference on one side. So we're not referencing it to ground, but we're referencing it over here at B. And then on the positive terminal here, we're referencing in the middle of this voltage divider. And obviously A is the one that's going to change because this strain gauge is going to change resistance, right? So we're still going to have a 10 volt drop on this branch and also on this branch. But obviously the node voltage at A is going to be different depending on what the value of that strain gauge is. So there are many more types of transducers that are used in industry, so I encourage you to do a little bit more research and see what you can find on these.